All right. So now we're going to use what we just found by solving for a particular solution to go from the exponential growth or decay to the actual equation. So it's going to be y equals. Now to represent the initial value, I'm going to abbreviate that as a sub 0. And then it's going to be multiplied by e to the kt. And these are the same k's. All right, so in the middle of these, I'm going to write that a sub 0 is the initial amount. When t equals 0. Now that has to be given to you for you to be able to do this shortcut. Now there's also a linear shortcut as well. All right, so it's going to be a linear equation. It's going to be y equals. Now for a linear equation, you have two things. You have the slope and you have the y-intercept. What do you think k is going to be? The slope. So a differential equation is always going to give you a slope. Okay, she's on her way. All right, and then what do you guys think the y-intercept is going to be? A sub 0. Good job. All right. So we are going to do example 1, and it's not going to feel like calculus. It's going to feel like algebra, really. So for example 1, the quantity R in grams of a radioactive substance decreases according to exponential decay model dr over dt equals negative 0.05 R, where t is measured in seconds. During an experiment, a scientist determines that the rate of decay of a second substance with the quantity S in grams can be represented by the linear model ds over dt equals negative 4, where t is measured in seconds. If at time 0, R of 0 is 100, S of 0 is 125, at what time in seconds will there be equal quantities of both substances? Okay, that's a lot of words. So let's just start off with R. I'm going to highlight the stuff that tells you things about R. Now, it tells you in the words that R is exponential decay, but we could know that if it didn't tell us, because for a differential equation, that the model is a number times a constant, and that matches with the numerator, then it's exponential growth or decay 100% of the time. So that is exponential, and then we know our initial value. So let's just go ahead and write our equation for R of t. We would start off with our initial amount, which is 100, and then E. All right, what's going to be our K? Good, negative 0.05 T. That's our equation for the exponential decay of the radioactive material. All right, I'm going to go back and highlight with green for S. So this is the information about S. It tells you it's a linear model. It doesn't have to tell you it's a linear model for you to know that. But you guys go ahead and take that differential equation and initial amount and write a linear model for me, please. So now what we want to do is figure out when these are equal. The quantities are equal in both your substances. Now this is a calculator question. Your calculator can do that really fast. What do? look at the graph and find where they intersect. So you guys go ahead and type these in y1 and y2 in your calculator, please. Now, you may have to change the window because there's a good chance there's a 100% chance if you're going from -10 to 10, you can't see anything. Why do you think that is? Okay, we're starting off at 100 and 125. So when I did this, I changed my x min to 0 and x max to 125. That actually doesn't matter. You can make it whatever you want to. The y, I would do the same as my x. So just to be safe, y min 0, y max 125. And I think you should see everything. All right, I'm going to pull up a Desmos graph. It's going to work a little differently than yours, but it will look the same. Okay, so these are the two graphs, our exponential and our linear. And we want to find where they intersect. So on Desmos, I can just push a button and, oh, it tells me, which is kind of cool. What do you guys have to do?
Second trace.
Very good. Second trace and number 5?
Yeah.
Yes, second trace 5. And hopefully you got the same thing I just got by clicking a button. All right, it tells us our time is in seconds, so label that please with seconds. All right, any questions on that one? So for the next one, that's the only one we're using the calculator on. And then on your assignment, the first one is a calculator and all the rest are non-calculator. So for example 2, the amount of a bacteria in a petri dish increases at a rate proportional to the amount present. At time t equals 0, the amount of bacteria in the dish is 10 grams. At time t equals 2, the amount of bacteria in the dish is 30 grams. What is the amount of bacteria in the dish at time t equals 6? Okay, it doesn't tell us that is exponential or linear, but it does tell us one statement at the beginning that we can write like we did when we first started this unit. So the amount of bacteria increases at a rate proportional to the amount present. So we could say that dB over dt is equal, proportional means we multiply K by the amount of bacteria present. All right, and that differential equation translates to exponential growth or decay. So we can go ahead and do that. So I'm going to say that B of t is equal, do we have an initial amount of bacteria? 10 grams. E, and then we do not know K. We are going to have to find K. Okay, and we did this almost exact problem in pre-calculus. So we know that at time 2, the amount of bacteria is 30 grams. So what we would do is put 2 in for time and 30 in for bacteria, for B. And we're going to solve this for K. What would you do first? Divide by 10. Nice. Okay. And then to solve by k, we have to get the k down. What do we use to get the k down? Natural log. Nice. Okay. The natural log of e cancels out. We're left with 2k. So natural log of 3. And then we'll just divide by 2. So k is this expression. If this is a non-calculator question, we can't do any better than this. This is all we can do. All right, so what I'm going to do is go back up to where I wrote my equation and replace k with natural log of 3 over 2. It looks weird, but we can do it. Now, if the question was just to write the model for B, you would be done, but we have to use it. So it asks us to find the amount of bacteria in the dish when, or at times 6. So we're going to put 6 in for T. Now this kind of threw some people off in my earlier class. Like they wanted to multiply the 3 times the 6. You cannot do that. The natural log of 3 is one number. Like it's some ugly decimal. But we can do 6 divided by this 2. What's that going to give you? 3. Good. So it's going to be 3 ln 3. Now we can actually get this down to just a number. Even though right now it seems kind of weird, we can use that property we just talked about, where if we have a number in front of the natural log, I can move it up to a power. All right. And then 3 to the third is 27. What do we get when we do e to the natural log of 27? Yeah, so it's 10 times 27. So eventually, we know that at time 6, there's 270 grams of bacteria. Now that wasn't, well, I pulled it from where I pulled my AP questions. So that was a question that we didn't really use calculus to do. It was just a whole bunch of algebra. We needed to know one part at the beginning, and from there it was just all algebra. It is a lot of algebra. So you guys all had a really good algebra teacher. Just kidding. I'm just kidding. You all did. All right, let's look at example 3. So during optimal conditions, this one is kind of crazy. The rate of change of the population of a certain organism is proportional to the population at time t in hours. At time t equals 0 hours, the population is 300. That's an important population. At time t equals 24 hours, the population is 1,000. And then we want to know at what time t is the population 500. Okay. So let's go back to the first sentence. The rate of change of the population is proportional to the population at time t. So that would be, we'll call P for the population is equal to KP. So definitely exponential. All right, so I could go ahead and say that P of t is equal to 300 e to the kt. Now the thing that's kind of crazy about this one is the numbers don't work out as neatly as the one we just did. So when I put in 24 hours and 1,000 organisms, it just doesn't divide out too nicely. So we get 10 thirds. when we divide. Okay, and then same steps. Go ahead and do the natural log. Bring your K down. And then divide by 24. And then I can go back to the beginning of the problem and replace K with that crazy looking fraction. All right, now this one also, not only does it not work out like neat, it also asks you to do something more difficult. So the last one, we were evaluating the function when time was 6. This one, we want to know how long it takes for the population to be 500. So it's just more challenging to finish. So we would now take 500, put it in for your population, and then solve this crazy looking thing for t. All right, so we kind of start off just like we did by dividing. All right, and then to get that t down, we're going to have to do the natural log. Make sure you make your division bar longer. Okay, we want to solve this for t. What would y'all do first? Multiply by 24, smart. Okay, and then divide by the natural log of 10/3. So that's what our t is, that crazy fraction. And when on a non-calculator problem, this is it. This is all we can do. What did you say? Now, the test I took this from, they actually wrote the answer, in my opinion, in a kind of a less normal looking way. So let me show you what they did. Because it was a multiple choice question. So would you guys be able to take this and know that that's the same? I hope so. It was really the only one that even looked close. So this, I don't know. I think at this point where I left it as a fraction, they did 1/24 natural log of 10/3. And so that it made more sense for the answer to look like that, but I don't particularly like it like that. So either way, I think you guys can match it.